Hey. Alright. We're going to do a session today on functions. Hopefully the slides that I prepared will give you a little bit more insight as to some of the different concepts that you need to be aware of when it pertains to functions. And if not, we'll definitely have the opportunity to go over any questions or anything you may have in class. Alright, so you see here basically we'll talk about X and Y, plugging in functions, determining solution, function tables, vertical line test, domain and range, so on, so forth. Alright, let's see here. Okay, go to our next slide. Come on, next slide. Beep. Alright, there we go. Is that right? No, that's not what I wanted. This is what I want. There we go. Alright. X versus Y. We talked about X and Y as it relates to graph, and we know that X is the horizontal axis and Y is the vertical axis of a graph. Well, here as it relates to functions, X typically relates to the input, or what we call the domain. Excuse me. Alright, the domain. And Y is what we refer to as the output or the range. But other commonly used forms of Y is f of X, g of X, h of X. And at the end of the day, basically when we're talking about Y, we're usually referring to the answer. Okay, so here I'm trying to show you that Y equals 3x minus 4 is pretty much the same as saying f of X equals 3x minus 4. So all we did was replace Y with f of X. Alright, they're interchangeable. Okay, and here's your quick little definition of a function. Relationship between an input and output that states that there can only be one output or answer for every given input. Basically, all we're trying to say here, let's go back to this function we have here, f of X equals 3x minus 4. All we're trying to say with this definition, alright, is that if I choose some input, let's say I choose to make x equal to 2. If I choose to make x equal to 2, I will plug it in right here where the x is. So instead of 3x minus 4, I have, that would be 3, times 2 minus 4. Alright, the x has been replaced by 2 because x is 2. So I replace the x with 2. So 3 times 2, which is 6 minus 4. So 3 times 2 is 6. 6 minus 4 equals 2. So my answer would be 2. So if I plug in a 2 for x, then the way I write it is f of 2 equals 2. So again, I replaced x with 2. So instead of f of x equals 3x minus 4, I now have f of 2 equals 2 based on plugging in the number 2. So I plugged in 2. I plugged in 2, x is my input, and I got an answer of 2. Answer is my y, alright, or my f of x. Now, again, going back to explaining this definition right here, all this definition says is as long as I plug 2 into this function, as long as I plug 2 in to this function, my answer will always be 2. So in other words, it would be impossible for me to say f of x equals 3x minus 4 and then now say f of 2 equals 3 times 2 minus 4, right? Because I've replaced the x with my 2. Alright, I plugged in my 2. And now, instead of saying f of 2 equals 2, now I'm going to tell you f of 2 equals 3. Alright, that's wrong. Does not happen. Alright, every time I plug in 2, I should get an answer of 2. Okay, so that there can only be one answer. There can only be one answer for any given input. So in this case, 2 is our input, and we can only get one answer when we plug that in. So every time we plug 2 into this function, the answer will be 2. Alright? Now hopefully as we continue to go forward, it'll clear it up a little bit, but again, that's all we're talking about with that definition. Alright. So I just basically showed you an example of what we're talking about here, plug-in functions. Okay, so plug-in functions. So we have our function f of x equals 3x plus 2. Find f of 5. So all we're saying is replace x with 5. So if I put a 5 everywhere x was, right, and I'm showing it to you in red, then I get an answer. So f of x equals 3x plus 2, put a 5 in, that's 3 times 5 plus 2. Then I get an answer of f of 5, because I replaced x with 5, equals 17. So 17 would be my answer. And every time I plug in 5, I will always get an answer of 17. It is impossible for me to plug in a 5 and all of a sudden magically get something different than 17. That's all we're saying about the definition on the previous slide. Okay? And then here I'm just showing you that y is 17, output is 17, range is 17. So that y is the same as output, which is the same as range, which is the same as answer. Okay? Here's another example. F of x, there you go, find f of negative 2. So all you're doing is replacing x with negative 2. X with negative 2. X with negative 2. Everywhere you see an x, you plug in a negative 2. Alright? So now you have a negative 2 squared, which gives you a positive 4. 4 times 2 is 8. And then you see a negative and a minus sign, which becomes a plus sign. So 8, alright, plus 2 is 10, right? Because that negative and minus sign becomes a plus sign. So the 8 you got here plus the 2 here is 10 plus 4, 14 is your answer. Alright? So that's all we're really talking about when we're saying plug-in functions. Okay? Alright. Now when it comes to plug-in functions, we could be asked the same thing. So let's say in this case, this line right here, the red line, represents some function. Alright? Some function. Whatever the case may be. Now, if you're actually given a graph, which this red line represents, this red line is a graph of a function, okay? The red line is a graph of a function, of some particular function. And what we want to know is, all of a sudden now we say, okay, well, what is f of 4? Alright, so now instead of saying f of x equals the red line, right, because the red line is our function, now we want to know what is f of 4 equal to. Well, anytime you're given a graphical representation of a function and they're wanting you to evaluate the function for some particular input, which is our 4 is our input, or our x, or our domain. Alright, so if we're given some particular domain to find a range for a function or a particular value for a function, then all we do is we remember that our input represents the x-axis, and this is our x-axis. So if x is now 4, if x is 4, then all we do is go to 4 on the x-axis. Here it is. There's 4 on the x-axis. Okay, so I want to know what is f of 4. Not 4, but f of 4. In other words, what is the answer, what is the output when I plug in 4? Okay, when I evaluate this red line, this function, at x equals 4. So all I do is I find 4 on the x-axis and I go from that to the graph. Okay, so I go from 4 to the graph. Now, wherever I'm touching the graph, then that establishes a point on that function. So now all I need to do is from that point draw a line to the y-axis, and that will tell me what my corresponding y value is. So in other words, when x is 4 for this red line for this function, y is 3, as represented right here. 4, 3. Okay? So when x is 4, y is 3. Alright? And I show it to you again here with the -6. So now again, my red line is a function. Doesn't matter, just some given function. They don't have to state it. You're seeing the graphical representation of it here. So we're given a graph, alright, and we know that is f of x. This graph is f of x equals something, right? Now, what we want to know is, let's say now we want to know f of -6. So now what we're wanting to do is replace x with -6. So if x is now -6, then I need to go to -6 on the x-axis. There it is. And from that, I need to go from the x-axis to the graph, wherever it may be. Notice over here, when we're at 4, we had to go up to get to the graph. Well, over here, we have to go down to get to the graph. So from our -6, we go down, and we touch the graph right here. So at -6 for x, our y, we just draw from the graph to the y-axis, and there you have it. Our y is right there at -1. Alright? So when x is -6, our y, our answer is -1. Okay? So that's an example of how to evaluate functions when you're given a graphical representation of the function. Alright? Let's see. Going forward. Here we go. That was 4. Come on, man. Alright, here we go. So 5. Alright, determining the solution. Okay. Determining the solution. This is pretty easy. Alright. And give you an example. There's 3, 2, right? There's a point. Remember, every point is an x and a y. Right? Every point is an x and a y. So it's 3, 2. X is 3, y is 2. Is it a solution for this function? Alright? So all you do is understand x is 3, y is 2. So where the x is, you put a 3. And where the y is, because remember, f of x is the same as y, you put a 2. So that's what we're showing you right here. Notice the 2 is in blue. There it is. The x was in red. The 3 was in red. There it is. So now what we're saying is, if I plug in a 3 for x and a 2 for y, or f of x, because y is the same as f of x, then 2 should equal what I get on this right hand side of the equation. 2 times 3 is 6. 6 minus 4 is 2. So 2 equals 2. 2 equals 2, right? This gives me 2 over here. So that means 3, 2 is a solution. Alright, and that's what I'm showing you. 3, 2 is a solution. Because when I plug in 3 for x, 2 for y into the given function, the right side equals the left side. It works. Okay? Now, let's look at the 1, 4. Alright, we have our function again. So my 1 is my x, so my 1 will go here, and my 4 is my y, or my f of x, so my 4 will go there. Okay, so now what I'm saying is 4 equals 4 times 1 minus 1, right? Because I plugged in a 4 over here too. So there it is. Alright, well, 4 times 1 is 4. 4 minus 1 is 3. So over here, I get 3. On the left side, I have 4. 4 does not equal 3. Alright, so when I plugged in my 1 and I plugged in my 4, I got an equation that does not equal out. So therefore, this point, 1, 4, is not a solution for this function. Okay? Again, I think this is pretty straightforward. Okay? Moving on. Alright, now, function tables. Now the ones I'll show you here in these next few slides it'll be arrow based. So when they're arrow based, there's a very basic way to look at them, or a simple way for me to explain it to you. But at the end of the day, what we're doing is we're going back to the notion that whatever number I plug in for x, I can only get one answer when I plug that number in. So let's say if I'm looking at this particular function here. Alright, so if I'm looking at this particular function and I decide to say my domain is 1, okay, when I plug in 1, alright, in other words, x equals 1. So if I plug in a 1 right here, I'm going to get 1 plus 3. 1 plus 3 is 4. So when I plug in a 1, my answer is 4. Alright, that's the understanding you need to have about the arrows. The x is saying I'm plugging in a 1 for my x, and my y, or my f of x, however you want to look at it, my y or my f of x is 4. Now, again, every time I plug in 1, if I plug in 1 again, the answer should always be 4. So in other words, it's impossible for me to plug in a 1 here and get the answer is 4, then plug in 1 again, but now all of a sudden get a magical answer of 5, right? I can't plug in 1 and get 2 different answers. Every time I plug in 1, I better get the same answer. It is impossible to plug in 1 and get 2 different answers. Okay? That's all we're trying to get you to understand here. Okay? So this table represents a function. So again, the exercise here is about looking at a table and being able to determine whether or not that table represents a function or not. And in this case it does. So in other words, if I look at this input, it only gives me one answer. Alright, and that's fine. When I look at this input, it only gives me one answer. That's fine. When I look at this input, it only gives me one answer, and that's fine. Okay, so this is good. This is a function. Alright, every input on this side has one and only one answer. That's all we care about. Alright, we can't have more than one answer for one input. Okay? Alright, let's see here. Oops, there we go. Alright, so again, back to the exercise. Now in this case, you're not given a particular function. Like in the last problem, you had f of x equal to negative x plus 2 or something. Here you're not given a function. You're just given a table. And you're supposed to look at this table and be able to determine if this table represents a function or not. It's irrelevant what the specific function is. All they want to know is that you have an understanding of what constitutes a function. So in other words, for every input, is there only one answer? Okay? So let's look at each input. When I look at this input, x is an input, a domain, right? When I look at 1, 1 only has one answer, and that's 4. When I look at 2, so if I was to plug 2 into a function, some given function, it only gives me one answer, 5. When I look at 3 for an input, for a domain, if I plug 3 into some function, it only gives me one answer, and that answer would be 6. So this is a function. This is a function, because every input has one and only one output, one and only one answer. Alright? Now, in contrast, let's look. here, again, we're not given a specific function, we're given a table, and we're asked to review this table and determine if this table represents a potential function or not. Alright, and again, all that is us looking at the domain, the X, the input side, and seeing if each input has only one answer. So when I look at the 1 has one answer. When I look at the 2, if you notice, has two answers. It has this 5, and the 2 has this 4 for an answer. So that right there tells me that this can't be a function, because it's impossible to plug 2 into a function and get an answer, and plug 2 into the same function and get a different answer. So in other words, if I have f of x equals x plus 3, let's say. Now, I'm going to plug in 2. So now we're going to say f of 2 equals 2 plus 3, right? Because we're replacing x with 2, right? We're plugging in 2. So now, when I plug in 2, I get 2 plus 3, so f of 2 equals 5. So when I plug in 2, my input is 2, I get an answer of 5. So that's showing that relationship right there. Now, based on this right here, this is trying to say now magically, if I take this same function, plug in 2 again, that somehow when I plug in 2, magically now the answer is going to be a 4. And we know that's not true. Every time we plug in 2, the answer is going to be 5 for this particular function. So it's impossible to plug in 2 again and now the answer magically be a 4. Can't happen. Alright, can't happen. That's why we say for every input there should only be one answer. Alright, now we don't care what the answer is as long as there's only one. Now when I look at the 3 only has one answer, and that's a 6. But the fact that this 2 had two answers, that told me that this was not a function. Okay, not a function. Okay, here's one that tends to trip people up. Alright, again, looking at a table, trying to figure out if it represents a function or not. We're not given any particular function. All we're being asked to do is evaluate each input and see if each input has one unique answer. So when I look at A, does A have one answer or more than one answer? Well, A has one answer, which is D. When I look at B, does B have one answer or more than one answer? Well, B has one answer, and it's D. When I look at C, does C have one answer or more than one answer? Well, C has one answer, and it's D. So as long as every input, every domain has only one answer, then it is a function. Alright, it doesn't matter that they have the same answer. All you care is that each input has only one answer. Alright, so this is a function. Okay, now I want to skip ahead for a sec. Let's see here. Okay, yeah. Go to this blank screen. Now, that what we just showed was one way to one view of tables. Now there's another view of tables, alright, that I didn't have in the slides, but I want to show you real quick. So let's say if we're given a different view, alright, f of x, x, f of x, x, f of x, x, f of x. Alright, let's say I have 1, 2, 3, 4, 5, 6, 1, 2, 2, 4, 5, 6, 1, 1, 2, 4, 4, 5, 1, 2, 3, 5, 5, 5. Alright, here we go. So now, this is a different look. This doesn't have the arrows. Alright, so when you don't see the arrows, then you're to understand that whatever input is on the left, the number directly to its right is its answer, is its output. So the left would be the domain, the right would be the range. So when we're looking at these 4 different tables, when I look at this first table, what this first table is telling me is there is some function, and we don't care what the particular function is. It just says that there is some function out there that when I plug in 1, I get an answer of 4. When I plug 2 into the function, I get an answer of 5. And when I plug in 3 into the function, I get an answer of 6. Alright, that's what this is telling me. So 1 gives a 4 for an answer, 2 gives a 5 for an answer, and 3 gives a 6 for an answer. Alright, now in this case, if you were being asked to evaluate this table and determine whether or not it is a function, the answer is yes, it is. Yes, this represents a function because every input had only one answer. This input had one answer. This input had one answer. So that's what made this a function. So yes, it is a function. Now when I look at the second one, again, this table is saying, does this represent some function? Well, I have to ask myself. It says when I plug in 1, I get an answer of 4. When I plug in 2, I get an answer of 5. Now it says if I plug in 2 again, now I'm going to magically get a different answer, which is 6. Alright, so this table is trying to make me believe that there's some function out there that I can plug 2 in and get an answer of 5, and then plug 2 in again, and all of a sudden now the answer is going to magically change to 6. Can't happen. If you want to see this in terms of the arrow, if this was the arrow that table that we were just looking at, let's say, then what this is trying to say is that my 2 gives me an answer of 5 and my 2 gives me an answer of 6, and we just explained that for every input you can only have one answer, and this is trying to say that for the input I'm having 2 different answers. That's what they're saying. This is the same input, so this is one input but giving me 2 different answers. Alright, can't happen. If I plug in 2, I better get 5 each time. Or if I plug in 2, I better get 6 each time. I don't care what the particular answer is, so long as it's the same answer every time I plug that input in. So every time I plug in 2, I better get a 5, or every time I plug in 2, I better get a 6. But I can't plug in 2 and get a 5 one time and then get a 6 a different time. Alright, it's always got to be 6 when I plug in 2, or it's always got to be 5 when I plug in 2. It can't be either or. Alright, so this would not be a function. Okay, now looking at this third one, this is saying that when I plug in a 1, I get a 4. If I plug in a 1 again, I still get 4. If I plug in a 2, I get a 5. This is fine, because what this is saying is, just like we said, every time we plug in 1, we better get the same answer. In this case, we plugged in 1, we got a 4, and we plugged in 1 for a second time, we still got a 4 for an answer. Alright, so this is fine. This input, the input of 1, has one answer. Every time I plug in 1, I get the same answer. So that's fine. And my 2 has one and only one input, which in this case is 5. So this is a function. The last one. This one tends to trip people up. Okay, we see these 5s here. So when I plug in a 1, I get a 5. When I plug in a 2, I get a 5. When I plug in a 3, and get a 5. Alright, now most people look at this and say it's not a function. But if you think about what we're saying every time you plug in a number, you can get one and only one answer. And what I'm saying here is when I plug in a 1, I get only one answer, which is 5. When I plug in 2, I only get one answer, which is 5. When I plug in 3, I only get one answer, which is 5. So this is fine. Again, if you want to see it in the arrow form, let's say I have my 1, 2, 3, 5, 6, 7, let's say. All this is like the problem where we said 1 gave me a 5, 2 gave me a 5, and 3 gave me a 5. And we said that was fine because each input, each domain only had one answer. So this is a function. This is good. Okay? This is a function. Alright? So I want you to understand that there's a different way for me to give you the table other than this use of arrows. Alright? And also, I could write these as actual points. So let's say this first table could be listed like this. And you'd be asked to look at A and say, is A a function? Well, every time I plug in 1, I get one answer. Every time I plug in 2, I get one answer. Every time I plug in 3, I get one answer. So this would be a function. B would be an example of this one. So I could have a 1, 4, a 2, 5, and a 2, 6. Again, all I'm doing is putting these in coordinate form and point form. So when I plug in a 1, I get a 4. When I plug in a 2, I get a 5. But I plug in 2 again, and now the answer is 6. Plug in 2 and get a 5, then plug in 2 and get a 6. Can't happen. Not a function. Alright? C. 1, 4. 1, 4. 2, 5. Alright, here they go. 1, 4, 1, 4, 2, 5. So when I plug in 1, I get a 4. Plug in 1 again, I get a 4 again. That's fine. Plug in 2, get a 5. This is a function. D. I have a 1, 5. I have a 2, 5. And I have a 3, 5. Alright, when I plug in 1, I get a 5. I plug in 2, I get a 5. Plug in 3, I get a 5. I don't care about the answer being the same so long as each of my inputs has one and only one answer. So again, that is a function. Alright, so now we've looked at different tables to determine whether or not what we're being given represents a function or not. So now what we want to do is determine whether or not when we look at a particular graph, is that graph representing a function. Alright, and when it comes to looking at a graphical illustration, we use what's called the vertical line test. And basically the vertical line test says when you look at a graph, so in these examples the graphs are the red lines. Alright, so the graph is the red. Okay, when you look at a graph, if it's possible for you to draw a vertical line anywhere on that graph and touch it more than once, then it's not a function. Alright, if you're able to draw a vertical line anywhere on that graph and touch it more than once, then it's not a function. Okay, so let's look at example A. Alright, the red is my graph. Now I can draw a vertical line right here, and I only touched the red graph right there, so I touched it at one point. Alright, so as long as I only touch it at one point, then it's good. But the vertical line test says that if I can draw a vertical line anywhere and touch the graph more than once, then it's not a function. So let's see. Well, what if I decided instead of over here, but over here to make a vertical line? If I make a vertical line over here, I'm touching the graph 1, 2, 3 times. And because there exists the possibility for me to draw a vertical line and touch the graph more than once, then that says it is not a function. Not a function. I could draw a vertical line here. It'd touch it 3 times. I could draw a vertical line there. It'd touch it 3 times. So even though I was safe right here, the fact that these other possibilities exist, the fact that the possibility exists to draw a vertical line somewhere and touch the graph more than once, determines that it's not a function. Let's look at B. Alright, you see right here, I've drawn a vertical line, and I've touched the graph, the red, more than once. I've touched it twice. If I drew it there, twice. If I drew it here, twice. If I drew it there, twice. Alright, so this again, not a function. Alright, let's look at C. I drew a vertical line right here. I touched the red line right there one time. Well, let's say if I draw one right here, I touch it one time. What about right there? One time. Here, one time. Here, one time. So it doesn't matter where I draw my vertical line, I'm only able to touch it one time, okay, with each individual vertical line. So this one actually checks out. This is a function, alright? This does represent a function, so that one is fine. Alright, looking here at D, drew a vertical line here, touched one time right there. Well, let's say, what if I drew it there? One time. Right there, one time. If I drew a vertical line there, it only touches one time. If I draw a vertical line there, it only touches one time. So this also represents a function, because anywhere I decide to draw my vertical line, I'm only going to touch my graph one time. So this is a function based on the vertical line test. Alright, moving on. Okay, now domain. Alright, when we're talking domain, we're basically talking about three cases in particular. And what we're wanting to do is we're wanting to say, if I'm given a particular function, alright, what can x be and what can't x be? Alright, what span of values can x be and what span of values can't x be? Alright, and so I've actually just broken it down into three main cases. Alright, in the first case, when you're looking at a function, alright, you have a function, f of x, g of x, h of x, whatever the case may be. When you have a function and it's written in fraction form, here, this is a fraction form, you have something over something, then the main thing you worry about when you're given a function in fraction form is you can't have 0 in the denominator. You can't get a 0 in the denominator. Alright, so if you're given a function that's in fraction form, what you want to do is identify what value or values of x will give you a 0 in the denominator. So in this case, I have 3 minus x, so I just say 3 minus x equals 0 and solve for x. Well, I can just add x to both sides and I get x equals 3. So in other words, if x is 3, then 3 minus 3 would give me a 0. So if x is 3, then I get a 0 in the denominator, and we say we don't want 0 in the denominator because a function is undefinable when you have 0 in the denominator. Okay, so the fact that you can't have a 0 in the denominator tells me that my domain is x, for x is x such that x cannot equal 0. Alright, so x can be all real numbers. It can be all real numbers. Alright, x can be all real numbers, but, and I messed up right here, I didn't mean to write 0, I meant to write 3 right here, right? Because we said if x equals 3, that gives us a 0 in the denominator. So x can be all real numbers such that x cannot equal 3. Okay, x can be all real numbers such that x cannot equal 3. Alright, and that's the one thing that gets us in trouble if the denominator is 0. So if x is 3, 3 minus 3 gives us a 0 in the denominator. So that's case 1. Now case 2 says if you're given an even root radical, square root, fourth root, sixth root, an even root radical, we don't take the even root radical, say the square root, we can't take the square root of a negative number. Alright, so when we're talking an even root radical, and this is really supposed to be drawn so that the whole thing is under the square root sign. Alright, so what will get us in trouble here is if x turns out to be any values that turns this answer in here into a negative. Okay, so well, we say, alright, the cutoff for negative is 0, right? Because once you go to the other side of 0, then you're in the negative territory. So we say 0 is our cutoff. So we say x minus 2 equals 0 to find what our safe spot is. So if you add 2 to both sides, x equals 2. So what that says is if x equals 2, 2 minus 2 is 0, I'm still safe. I'm safe when x is 2. Alright, 2 is a safe spot. Now, what I need to figure out is when I go the other side of 2, okay? 2 is my safe spot. Now, if I go up to 3, what'll happen? Well, okay, let's say if I go up to 3, if I plug in a 3 for x, 3 minus 2 gives me a 1. So that's a positive number. Alright? So if 2 is my safe spot, and if I go up to 3, or let's say I go up to 4, if I plug in a 4, 4 minus 2 gives me a 2. 2 is positive. So it looks like I'm safe at 2 and anything bigger than 2. Alright? Now, let's look at 1. If I plug in a 1, let's say, 1 minus 2 gives me a negative 1. Alright? So now what we're seeing is if we get less than 2, alright, 1, 0, negative 1, whatever the case may be, that's when we get into negative territory under here, and we say we can't take the square root of a negative. So the way we say this is the domain for x is all real numbers such that x must be greater than or equal to 2. X is all real numbers such that x is greater than or equal to 2. X is greater than or equal to 2. Alright? Because we see here if x is less than 2, 1, 0, negative 1, if we plugged in anything less than 2 for x, we'll get a negative value under the square root sign, and we can't take the square root of a negative. So this would be an example of our domain. Okay? So that's what we're saying down here. Alright, now the third case is just a combination of case 1 and case 2. So it says what happens if you have the square root in fraction form. Alright, so we see that fraction form, so no, for the bottom we don't want a 0, so x can't be 3, because if x is 3 we get a 0 in the denominator, so that's case 1. And we have the square root in the top, so for case 2 we're worrying about a negative. So here we're saying for the top x has to be greater than or equal to 2. For the top, for this part, x has to be 2 or greater. So when you combine the two situations, you have an even root radical in fraction form. Then what you have to do is you have to look at your two independent solutions and bring them together. Alright, so for the radical part it says x has to be greater than 2 or equal to 2. For the fraction part in the denominator says x can't be 3. Alright, so now what we want to do is see if these two answers have any conflict with one another, and we see that right here we're saying x can't be 3, because if x is 3 it ruins us right there. Well, up here we're saying x is fine as long as it's bigger than 2. Well, we know 3 is bigger than 2, but right here we're saying x can't be 3. Alright, so this is in conflict somewhat with that, because this says x can't be 3, but here we're saying x is fine as long as it's equal to or bigger than 2. Alright, so the way we write it is x can be all real numbers such that x is greater than or equal to 3, but x cannot equal x is all real numbers such that x must be greater than or equal to 2, but x cannot equal 3. Alright, so we bring them together. Alright, we say x is going to be 2, or it can be any number bigger than 2. So it can be 2, 4, 5, 6, 7, 8. It could be 2.1, 4.3, 5. It can be everything except 3. Can't be 3. It can be 2 or anything bigger than 2 except 3. Alright, based on combining those two conditions. Alright, and that's what we're talking about with finding the domain if we're presented actual functions. Okay, moving on. Alright, now listing the domain if we're given an actual graph. Okay, now this can be a little tricky, so stay with me. If we're wanting the domain, remember domain is x. X is domain, so x is horizontal, right? X is the horizontal axis. So what you want to do when you're talking domain is you want to start at the farthest left and work your way right. Alright, and again, my graph is in red. So when I look at this, I say the farthest left I see in red is right here, which is right here where x equals negative 1, 2, 3, 4, 5, 6. So right here at negative 6. This is my smallest value of the red. Right there. So it starts at x equals negative 6. And now from here, as I read to the right, from here, I'm good. As I read to the right, I'm good here. Because look, here, 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 here. As I go right, I see that I have a continuing line. Alright, so I'm good as I go to the right until I get right here. Alright, it breaks, but guess what? It picks up right here at the same number, so I'm still good. So I can keep going. Alright, because red exists for all of these values as I'm going to the right. In other words, if I go from the x-axis, I can touch red anywhere from here on. So I keep going, because look, I can touch red here, I can touch red here, I can touch red here, touch red here, I can touch red here, I can touch red there, touch red, touch red, touch red, touch red. So I'm good. I'm over here now. I can touch red, touch red, keep going, can touch red, can touch red, keep going, can touch red, can touch red, can touch red. Oops, right here. If I go right past this right here, past here, I can't touch any red. Can't touch any red in here, anywhere. So that's the open space. So my x started at negative 6 and was good all the way up to 1, 2, 3. To x was a positive 3. So I was able to touch red from negative 6 left to right all the way to positive 3. So that's what I'm showing you when I say x is greater than or equal to a negative 6 and less than or equal to 3. X is greater than or equal to a negative 6, less than or equal to a positive 3. That covers all of this area right here. Because anywhere in here, I can go from my x-axis and touch red. Now, when I jump on the other side of this 3, I can't touch any red right here. I can't touch any red again until I get, bam, right here, where x is 4. Now I can touch red again. I can touch red, I can touch red, I can touch red, I can touch red. And I'm able to keep touching red until I get right here. And this is where it stops again. So that's x is 4, 5, 6. So that's at x is 6. So now I say, okay, I was able to touch red from negative 6 to 3 continuous. And I'm also able to touch red from 4 to positive 6. So negative 6 to 3, x is in between all of that, and x is in between and equal to 4 and 6. Alright, so when we're talking domain, we're reading left to right, and all we're trying to do is say if we're anywhere on the x-axis, can we go up or down and touch the graph. So here I'm showing you I can go down and touch the graph, go down, touch the graph, doesn't matter, I can go down and touch the graph, I can go down and touch the graph, still touch the graph, still touching the graph, come over here, I'm still touching the graph, I'm just going up now, but I'm still able to touch the graph. I'm not able to touch the graph leaving the x-axis anywhere in here. If I was right here on the x-axis and I went up, I wouldn't touch anything red. If I'm right here on the x-axis and if I went down, I'm not touching anything red. So this is a gap in here. Okay? So this space is a gap. So it's not accounted for, but guess what? As soon as I get here to x is 4, I'm touching red again. I'm touching red. I'm touching red. I'm touching red. And I'm able to touch red all the way up until I get to 6. Once I cross over 6, out here, I'm not able to touch any red anymore. Alright? So that's what I'm demonstrating here. Alright? Now, moving on. That's domain, which is the x-axis. So now we want to say, okay, what about range, which is the y-axis? Alright? So range, which is the y-axis. Okay? So now when we're talking range, range is y-axis, right? So when we're talking the y-axis, we're talking vertical, we're talking up and down. So now instead of reading left to right, we're reading from bottom to top, all right, along the y-axis. So I want to say, okay, where is the bottommost point or portion of red that I see? Okay, bottommost portion of red I see, the lowest point of the graph. Well, I see red right here. Alright, so from here, now we're on the y-axis, so all we're trying to do is say from the y-axis, can I go left or right and touch the graph? Well, from here I can go left and touch the graph, but if I go up just a little bit above it, I'm not able to touch any graph left or right. I'm not touching any of the graph left or right. I'm not able to touch the graph. I'm not able to touch the graph. I'm not able to touch the graph again till bam, right here. Now I'm touching the graph again. Alright, going left or right. When we're talking range, we're talking up and down. So now we use the y-axis and we go left or right from the y-axis to see if we touch the graph. So here, and I'm still going up, able to touch the graph, touching 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 the graph. I'm going right now, touching the graph, touching the graph. From the y-axis, touching the graph, touching the graph. And guess what? Bam. Right there. Okay. And if I could continue and be right here, and I'm touching the graph. Down here, I was at, let's see, that's 1, 2, 3, 4. So that was y equals a negative 4. This was y equals a negative 2. And this is 1, 2. This is y equals a positive 2. Alright, so the way we explain this is your range y equals negative 4, because right here we're showing that we're only able to touch the graph right at negative 4, not a little bit above it or a little bit below it, just right there at negative 4. Then it stopped. It didn't pick back up until we got to y equals negative 2. Once we got to y equals negative 2, we were able to go. We were able to touch the graph, right? We were able to go from the y-axis and touch the graph. Okay? So we said, all right, from negative 2, y was continuous. We were able to continuously be able to touch the red until we got to y was a positive 2. So we write our positive 2. After y is positive 2, once we get above positive 2, notice we go left, there is no red. We go right, there's no red. Left and right, I can't touch any graph, any red. There's no graph to be touched, no red to be touched as I go above y equals 2. Alright, so this represents our range. Alright, and there it is for you right there. Okay, so that was a I guess a crash course on functions. We won't cover this in particular in class. However, after going through this, if you have any questions or anything, I'll address any questions that may come up in class time. But it is on you to go through this, take good notes, and do your best to make sure you have a firm understanding of the concept of linear functions. Alright, so at this time we will conclude the session.